atoms exist. This was declared by John Dalton in his atomic theory at the turn of the 19th century. The implications for experimental chemistry were huge. The rate at which new elements were discovered and their unique properties characterized accelerated. We now find ourselves at the historical cusp of one of the great discoveries of chemistry, and it's one of the most iconic and useful tools we have as chemists: the periodic table.
In 1869, independent of one another, the Russian Dmitri Mendeleev and the German Lothar Meyer began listing and organizing the elements into a beautiful and amazing structure we now call the periodic table. Their criteria for ordering the elements were to list the atoms by increasing relative atomic mass and by common chemical activity. If discrepancies were found, the second criteria of ordering the elements based on chemical activity would trump the rule for ordering elements by relative atomic mass. Now let's begin lining up the 18 smallest and lightest elements regarding their relative atomic mass, starting with the smallest known atom, hydrogen. Also notice the symbols that we'll use. These symbols will become the shorthand used to describe the elements. Now, we begin grouping elements that have very similar reactivity and properties. We quickly see that hydrogen is unique, so we'll just place it alone in its own group for now. Helium, neon, and argon are all gases and not reactive at all, and they go together. Lithium and sodium both react violently with water, making hydrogen, and make the water bitter and basic. Beryllium and magnesium also react with water, but not as violently, while fluorine and chlorine are diatomic gases and are very reactive with most other elements, and so on. And we end up with the following chemical groupings for the elements shown in the slide. Now, it occurred to the table makers that if you ignored hydrogen and helium, every eighth element in the list has similar reactivity. Thus, the periodic nature of the elements began to reveal itself. It made sense then to line up the elements in the following way, with the columns being elements with similar reactivity. Helium has similar reactivity as neon and argon, so it was natural to put it in the same column as those elements. Again, where do we put hydrogen? Well, over the years, it's migrated to the first column on most tables, but we know it is unique. Anyway, the periodic table was born. When looking at the modern periodic table, you see for each element a number in the top left corner, which denotes the atom's unique atomic number for that element. Looking closer at the table, we see that each element is shown with its name and atomic symbol, and at the bottom is shown the relative atomic mass number based on the carbon-12 atomic standard. The oxygen standard was abandoned in the 60s. Now, almost all of the first 92 elements up to uranium are naturally occurring. The rest are synthetic elements produced and identified in high-powered labs. A parenthesis around the relative atomic mass number usually means that for these elements, because of the atom's unstable nature and the lack of knowledge about its isotopes, again, we'll talk about isotopes in another lecture, there is considerable error in obtaining its relative atomic mass value. Now, looking at the full periodic table, we can see instances where it seems the ordering based on relative mass did not make sense. Cobalt, Co, has a relative atomic mass of 58.93, and nickel, Ni, has a smaller relative atomic mass of 58.69, but nickel was placed after cobalt on the table. Cobalt behaves chemically like the elements right below it, rhodium, Rh, and iridium, Ir, while nickel behaves chemically like palladium, Pd, and platinum, Pt, the elements immediately below it. Remember, the authors of the table put a premium on chemical reactivity ordering over the ordering according to relative atomic mass. A column of elements is called a family or group of elements and have similar chemical reactivity and physical properties. A row of elements is called a period and are numbered with a 1 at the top to 7 in this table. There are also 2 rows containing 14 elements each at the bottom of the table. Now, if we had enough space on a piece of conventional 8.5 by 11 paper or a single computer screen, we would have placed these elements somewhere in the middle of the table. But to do so, we would have to shrink the font and the graphics to almost an unreadable size. So the compromise is to use an asterisk symbol on the table to signal where these elements should have been placed if we had more room on the screen. This wonderful chemical instrument shows a wealth of chemical trends and patterns within its arrangement of the elements. Let's first look at some broad classifications of the elements and their location on the periodic table. One way to classify the elements is to identify them as metals, nonmetals, and metalloids. Metals, these elements are hard, shiny when polished or cut, conduct and transmit electricity and heat rather well, are malleable and easily pounded into different shapes, fusible, and can be drawn into thin wire, a property we call ductile. We see that metals dominate the left side and middle of the periodic table. Nonmetals, well, these are elements that are usually easy to vaporize, are not very elastic, and do not conduct heat and electricity very well. Non-conducting substances are called insulators. These elements tend to be in the upper right corner of the periodic table. Metalloids, well, these elements are found on the periodic table at the interface where the metals and nonmetals meet. As would be expected, they have mixed properties. One of the most useful properties of these interesting elements, especially in this age of electronics, is their partial conductivity of heat and electricity. We call these hybrid elements semiconductors. Elements can also be categorized as main group elements or transition elements. Transition elements are more commonly called transition metals. Now, main group elements have well-defined and unified physical and chemical properties when comparing elements down a column. In old American periodic tables, the main group elements were labeled with a number or Roman numeral and the letter A. The set of elements in the middle are our transition elements, which have less predictable properties when looking at the groups or columns of elements. These groups are labeled with the number and the letter B. Though if you look closer, we see the numbers are out of sequence. The modern labeling of groups has abandoned the AB symbolism and simply number the groups of 1 to 18 going from left to right. Now let's turn our attention once again to the bottom 2 rows on the periodic table. Now, as we mentioned, these elements, many of them discovered rather recently or created in labs, would normally be placed in the middle of the periodic table, but there just isn't any room. Notice they do not have group numbers but have unique row classifications. The top row is called the lanthanides series, named after the first element in the row, lanthanum, and the second row is the actinides series, named after its first element, actinium. Now, how these elements are presented in the periodic table is a bit controversial. Most periodic tables, including your textbook, I would imagine, places lanthanum and actinium in group 3b, with the lanthanide and actinide series of elements placed underneath. The implication here is that all the lanthanide and actinide elements are in group 3b, since all these elements have very similar chemical properties. This ordering seems more in keeping with the ideals of Mendeleev and Meyer that put a premium on grouping elements according to reactivity. Now, my favorite table has a slightly different arrangement of these elements, leaving a gap for the elements lanthanum through ytterbium in period 6 and elements actinium to nobelium in period 7, placing lutetium and lawrencium in group 3b. This ordering, as we will see later, is a bit more consistent with the filling of electron shells, something we'll be doing soon. That being said, if I were consistent with my periodic table, helium would be next to hydrogen in group 2a, but I just can't do that. Helium is just too obviously like the group 8a elements chemically, so I can't bring myself to place it in group 2a column. But once again, we see that hydrogen is a unique element in nature and isn't included in any groups chemically. It's not like the group 1a elements as far as reactivity. There are tables that have hydrogen by itself, stranded at the top and middle of the periodic table. Another way to talk about the ordering of the elements in the periodic table is by special group and family names. Now, as we learned before, group 1a elements are highly reactive elements, and when thrown into water, react to produce hydrogen gas and make the water basic or alkaline. This column of elements is called the alkaline metals. Group 2a elements are not as reactive but still make hydrogen gas and a basic solution when thrown into the water. These are called the alkaline earth metals. On the nonmetal side of the periodic table, the group 7a elements are reactive elements called the halogens, which means salt-making or producing. These elements were originally found in salts. We also know that all these elements in their gaseous state form diatomic gases, F2, Cl2, Br2, and I2. Group 8a elements are highly stable monatomic gases known as the noble gases. The stability and lack of attractive forces between the atoms of these gases, especially for helium and neon, make them great experimental models of near-ideal kinetic molecular theory gases, gases which closely follow the ideal gas equation of state, PV equals nRT. Many times the groups are named after the top element in the group, such as a group 6a, which is known as the oxygen group. This particular group is also known as the chalcogen group, which roughly means copper-borne. Of course, we have many more group number elements, as well as our old friends, the transition metals and the lanthanide and actinide series of elements. And last but not least, our lone hydrogen atom. It is always handy to know as many of the elements, names, and symbols as possible, but to know them all is a tall task. I know that I don't have them all memorized. The list shown on this slide would be a great set of elements to put in the old memory banks. And also, we need to be able to place their location on the periodic table. The ancient or original name for some of the elements is included in parentheses, which also serves as the origin of the symbol that is commonly attributed to them. For example, tungsten's atomic symbol is actually W because its ancient name is wolfram.
From the rather rough description of the elements and matter in ancient times, we've now developed a systematic and organized periodic table of elements that make up the matter we'll be studying in chemistry. Now, as we progress in our understanding of chemistry, we will come to rely heavily on this powerful chemical tool. But we haven't scratched the surface of its true value and predictive power yet. But first things first, we need to figure out the underlying reasons why the elements form the periodic columns and rows on this table in the way they do. The answer to those questions should be the key to understanding the factors that govern chemical reactivity itself. Well, we'll see you next time.